Hello, my name is Sheraz, and I would like to present to you the Image EXIF Data Analyzer and Categorizer. This course was offered in spring of 2018, and this is our fabulous teaching staff. Kudos to them. Basically, what I wanted to do was all images have a hidden file which contains all the camera settings that were used to take the photo. Given a directory, I wanted to scan all the images found in that directory and then read all that EXIF data into a data frame. I have close to 1 million images and I take around 60,000 images a year. So it's important for me to do a bunch of automation. My images do have some categorization labels associated with them, so I wanted to see if the EXIF data could be used to predict what type of label should be associated with the image. I use the following libraries, OS and sys to read the images from the file system, PIL to actually read the EXIF data from the images, and math, because believe it or not, a lot of math is required in photography, and all these libraries to do visualizations. You can download all the files necessary from the below GitHub. This project would not be possible without all the help of the teaching staff and the students, and Stack Overflow and the internet, which always came to my rescue. Here is the project notebook. This function scans the OS. These are the file names that are going to be included, and this is the directory that's being scanned. This function for all the files found reads the EXIF information associated with them. I call these functions and load the data into a data frame and also load it into a CSV file. And I end up with 13,200 photos and 75 columns worth of data. This is what I think of EXIF data. Every manufacturer likes doing something different, and even though it's supposed to be standardized, it really isn't. After some research, I could remove all these columns before I even started doing other extensive data cleanup. I removed some columns based on the model, and then Canon did not store the focal length in the appropriate column, so I copied it over to the right place. Removed rows that had been editing using software because that might throw off my analysis. Also, based on my file names, I can label what type of image it is. So it's some baby, all baby, copy documents, and random images. And these are going to be my labels. Also, EXIF stores all data in tuples. So 2.8 is actually stored as 280, 100. So this function is applied to the entire data frame and converts everything to decimal places. This is math, believe it or not, and it took me a while to figure out how to calculate all of this. The main value of concern in the apex vals function is BV, which is the brightness, calculated from all these other variables. I ended up not really using exposure val. Depth of field is extremely complicated to calculate. C is actually circle of confusion, and believe me, it is confusing. I then applied these values to the data frame. I binned some of my data, like the hours and the brightness. I encoded, using the label encoder, some of the text-based fields. I removed some other columns and reordered the data frame so that everything was in the right order. This is the shape of the cleaned data frame. It's about 1,000 rows shorter and many columns shorter. Here's the description. This is a Seaborn plot. No real takeaways, but it's good to visualize the data. I made many of these graphs. This one is related to brightness, but there are many more in the notebook. I split the data into training and testing. I used the decision tree classifier with a max depth of 5 and min leaf of 275. You can see the decision tree classifier has got an accuracy of 67%. I could actually get it to 80% by overfitting the data. Here is a map of what the decision tree looks like. You can see that I've added the predicted values from the decision tree to the data frame. Here's an all baby in a some baby, so it's predicted to be all baby. And when we look at that file, we do find a cute baby. I did try some of the other models. Perceptron had an accuracy of 0.63 and Naive Bayes had an accuracy of 0.33. K-means confirmed that there were only 3 clusters. Thank you to the staff and students of CSCI E29.